One of the sort of interesting things about the sort of before and after framing is that there are often cases where you can identify that the kinds of interactions involved don't result in changes in one or the other of a conserved quantity. So let me give you some examples of when before and after framing is particularly useful. And I want to first think about energy a little bit, because if you think about energy, and particularly think about work, there are some certain characteristics that are useful to keep in mind. Energy is useful in before and after framing, first of all, if you have a purely conservative system, right? That's one example where it's useful because if the system is conservative, that means that the total energy before is equal to the total energy after. So you can always use energy conservation for any event that involves just conservative forces. But more than that, there are actually plenty of other types of interactions where you can still think about energy utility, even if the forces involved, they're not all what you would typically call conservative forces. In particular, anytime that the forces are all perpendicular to the velocity, whenever forces are perpendicular to the velocity, if you think back to power a little bit, these forces that are perpendicular to the velocity, right, are forces that actually don't transfer any power to the system. So if you think about, for example, a case where you've got a force that is always perpendicular to velocity, like the Magnus force, right? The Magnus force, that force is proportional to the cross product of the angular velocity and linear velocity. In other words, the Magnus force is always perpendicular to the velocity of the center of mass. Since the Magnus force is always perpendicular to the velocity of the center of mass, the Magnus force cannot actually cause a change in what the kinetic energy of the system is. So it can't do work on the system. And what it can do is redirect the direction of the velocity, but it can't actually do work on the system. And so to that extent, the Magnus force is an interaction that you can actually often think about productively from a before and after framing if you're thinking about energy, even though it's a kind of a complicated force. Certainly you also often deal with interactions, sort of events, that are more or less elastic. So when you talk about an event being an elastic event, that's actually saying it's one in which the energy before is equal to the energy after. But if you think about a sort of range from elastic to inelastic, you'll often find things where you have some sort of coefficient that'll tell you, like a coefficient of restitution, that tells you what the percentage of energy is that's lost. So even when you are losing some energy, often the idea of before and after framing is useful because of the fact that you can talk about how much energy was lost. If we talk about angular momentum, on the other hand, there are also plenty of cases when angular momentum is useful from a sort of before and after framing perspective. Certainly whenever there are no torques that are applied, that's going to imply that there's no change in angular momentum. And you might say, well, when are there no torques applied? Well, one pretty common example of no torques being applied to a system are when you're talking about central forces. Okay, so for example, if I talk about a gravitational interaction, right, so here's the Earth, here's a satellite out here, the gravitational force is always inward, right? And so if I try to define this as being my origin, R cross F is always 0 for any central force, so long as I choose my origin appropriately, which in turn means that no matter what path this satellite follows, its angular momentum is always going to stay the same. So whether it actually goes in a circle or whether it goes in some, ellipse or whatever path it follows, it's still at every single point on this trajectory going to have the same angular momentum. And that's actually pretty interesting because it allows you to very quickly figure out what this trajectory looks like. And in fact, this is part of the idea that if you look at Kepler's laws, this idea that angular momentum is conserved for a central force is a sort of key idea that's applied there. So when you look at a system, you can often identify whether or not it makes sense to use before and after framing by not just asking are all the interactions conservative, or are there no torques involved, but by thinking more about what the interactions are and whether the nature of the interactions are such that they can't cause a change in energy or can't cause a change in angular momentum. So for example, you can have forces that cannot cause a change in energy, and you can also have forces that do not cause a change in angular momentum. So looking critically at your system to figure out what can change and what can't change is pretty useful. I'll leave you with one other example of that, and it's a linear momentum example. Right. So if you think about some collision, right? Let's say I've got an object that's traveling along here, it hits some other object, right? And you sort of zoom in and you ask the question, what's actually going on there? Well, what's going on is that I've got one object touching the other object, and the force that it's exerting is a normal force. So in this particular interaction, one of the things I would be able to say is that, yes, the momentum of this object changes and the momentum of this object changes, but all the change in momentum must be along this direction, right? So there's a change in momentum along this direction. So let's say this direction is c hat for contact, right? Or actually, let's call it n hat, right? That's the normal vector to the surface here. So the change in momentum is in the n hat direction for this interaction, and there's zero change in momentum in the t hat direction, the tangential direction, right? So in the same way that you can sort of look at forces and ask the question, does that cause a torque? Or in other words, how is that going to change the angular momentum? You can also think about interactions and ask in what ways will those interactions change the linear momentum. And so if you've got, for example, collisions, you can look critically at this and say, well, the impulse has to be in the normal direction, so therefore the momentum only changes in that normal direction.